So the next part of this is going to be explaining how we model rotations. There's two different ways you can do this. I won't get too much into the details, but you can create a matrix. So if you have a 3 by 3 vector, break this down to Vx, Vy, and Vz. This is just a vector and arrow in 3D space. You got 3 axes. Now you can create a matrix, which is this big array of numbers, and you've got 3 dimensions, so you have 3 by 3 or 9 total numbers, and then the multiplication of this matrix by the vector will produce the rotated vector. Sometimes we'll just call this vector v hat, and then we have the r is the rotation matrix, multiply it, and then this rotates it to a different position, and that's the action of r on. You can think about the rotation matrix as actually rotating the entire space, but if you just plug in one vector, you get its rotated image as an output. The downside with this is that when you take a rotation matrix, even if you choose a really nice axis that makes a lot of these numbers 0, when you plug this into a computer and use floating point numbers, you get error accumulation, because there's a lot of extra degrees of freedom in here. You only have 3 dimensions of space and you're modeling a rotation, but because of the reality of floating points, small errors can accumulate. And the thing about matrices is they don't just model rotation, they also model stretching. So what will happen is a lot of these other values in the matrix will start to accumulate floating point error, and that will manifest as the object shearing and stretching over time, and that's something that you want to avoid. So the way to solve this problem is to model rotations with a type of number called a quaternion. Quaternion is this, well, I'll show you. If you wanted to just take your vector, which has Vx, Vy, and then Vz, you can create, you can use these things that are kind of like imaginary numbers. So you've got I, J, and K, and I did these in bold because these things right here, these I, J's, and K's, are actually not real numbers. They have the property that if you were to square one, if you were to square any of them, they become -1. And the reason this is useful actually is related to imaginary numbers in on the complex plane. So it's kind of easier to understand this when you go back to complex numbers. With complex numbers, if you were to take just the number I, you square it, you get -1. And then, so you can write all the numbers, all of the real numbers, when they interact with any imaginary numbers, you get a whole set of numbers. After you take the completion of all the possible combinations, you'll end up with these numbers that are of the form A plus B times I. And the way to visualize this is you've got an imaginary dimension, and then you've got a real dimension. And then, so here's the real line, right here, it's like the x-axis, and the real line right here is your A. So this is your A number, is going to be some coordinate on here, A. And then B is going to be some number on here, on the imaginary axis. And then now you can actually describe points with a single number. And why this is interesting is that you can take your number in a rectangular coordinate system, A plus BI here. And because you can also multiply these numbers, when you multiply them, something interesting happens. If you were to just take any complex number anywhere on the complex plane and then multiply it by an I, the action, like once you work out all the algebra, it turns out to have rotated it 90 degrees, which is really cool. So the action of I rotates it 90 degrees like that. And this is something that if you were just cranking through the algebra, it would be very surprising, like if you didn't already know this fact. So this is, here the i's, so the I times I is going to be negative, so you have -b plus A times I. So you get this 90-degree rotation when you multiply by I. And it turns out more generally, you can actually take any complex number here and decompose it into a form where multiplication becomes trivial. So instead of multiplying and then applying this rule here, you can express this complex number in a polar coordinate system. So if you were to take e to the I times theta, and then there's a radius. So this e to the I turns out to decompose into sines and cosines. We're not going to get into that now, but basically there's an equivalence between these two different forms of complex number. This one right here, the rectangular, a plus bi, makes it really easy to do rectangular coordinates. And then for the polar coordinates, the rotation is trivial as well, because when you multiply these two numbers, you just add the angles. So you can come up with arbitrary rotations and express them as a complex number multiplication. So when you add there was a guy named William Rowan Hamilton, who was trying to figure out a three-dimensional version of complex numbers. And long story short, he ends up discovering that you can't make a three-dimensional version of this complex plane work, that you always get a fourth dimension that pops out. And then that's because when you try to add a second imaginary number, you always get this third. It just pops out of the equations, and that's k. So, if you can model the rotation axis as these three imaginary dimensions, and then the fourth dimension, you can model it as your angle. So, for our purposes, the quaternion is going to look like this. You're going to have an angle s, and then you'll have three real numbers that represent your rotation axis. And the reason this is useful for computing is we don't have these extra matrix fields that can accumulate error. We only have error in the three dimensions that we're interested in. So we can really, really keep tight bounds on the error, and then it also is less data, so the object is smaller. And you can even take a single 64-bit number and pack 16 bits for each of these. So you could have 16 bits for your angle, 16 bits for each of these, and that means that you can actually get quaternions packed into an int. You just have to do some clever encoding. So that's kind of the big idea behind quaternions, and we're going to be using that for modeling rotations.